Well, hello everyone. Welcome to another exciting Data Viz Friday. We have, as always, the amazing Elijah Meeks here with us. I am Dave, Director of Product here at Notable, and today we'll be talking about distribution charts and how to understand how best to use the variety of different distribution charts that we have within our Data Explorer within Notable. So that, I'll kick it over to you, Elijah, and tell us all about distribution charts.
Thanks, Dave. So yeah, we've got, as usual, we've got an interactive notebook that I'm going to walk through. We've posted the link, hopefully, in all the places where we posted a link to this, but we'll also leave it as a comment on the YouTube video when the YouTube video is saved after the live stream's done. So let's just jump right into it. Distributions are an interesting pattern that we always want to look at with data visualization. And distributions to me are particularly interesting because we usually have one way in mind that we're going to look at distributions, depending on where you live in the data visualization ecosystem, depending on what your role is and what your audience is. You've probably got to go to visualization distributions. And so we're going to talk about 6 different kinds of distributions in this live stream: histograms, heat maps, violin plots, box plots, ridgeline plots, and horizon plots. Some of these hopefully are familiar to you. Some of them hopefully are not familiar to you, so you can get something out of this. We're going to talk about the structure of distributions, of distribution visualization, and what it's showing and how you can optimize the patterns for your audience depending on where you deploy these visualizations, whether you're using them for yourself or whether you're using them in explanatory graphics. So first off, let's talk a little bit about the data that we're looking at. Let me go pull this open and pull up a table real quick just so we can see what this data looks like. It's a very small data set that I have exploded into individual points. So this data set's a kind of famous data set of survey. 46 recipients, asking them about different natural language expressions of probability and asking them what those probabilities map to in their mind as far as a percentage goes. So we have statements like almost certainly, or probably, or unlikely, or little chance. And then we've asked the respondents, hey, when you hear the term almost certainly, what percentage do you think of? And so somebody said, well, I think of 95%. And when they hear the term we doubt, they think 40% and probably not as 15% and so on. So as you might expect, because we're human beings, when we start to look through this data set, we see that different people have different responses as far as what percentage associates with one of these terms. And so one of the ways that we can explore this is using these distribution visualizations. But before I get into those visualizations, I want to look at this as a scatter plot to begin with, because a scatter plot's really commonly used visualization, and you often see scatter plots used for distribution like exploration. And so if we plot all of these responses and we take the participant number as the y-axis, so each participant, we didn't record their names, or the survey didn't record their names, they instead record a number indicating the participants, indicating the participant. So you have participant 1, you have participant 5, and so on. We can see something about this data set. We can see something about the patterns in this data set. The thing that jumps out to you the most is right in the center here, about even, the term about even, as you might expect. Most people put that somewhere around 50%. That's pretty good, right? That seems like we're all in agreement around what about even means. And then we can see in the way that each of these is colored by the expression, we can see in the patterns in the scatter plot that there is some disagreement about what the percents mean for each of these expressions. You can see some strange outliers, like somebody thinks that we doubt means 100%. And so you could imagine what this respondent was thinking, that they might think that maybe they're 100% sure that they doubt it, or maybe they just clicked the wrong side of the scale when they were responding. So you can see some data here, but what you can't see, it really is the distribution of this data across each of these expressions. And the reason you can't see it is, first of all, we don't have any good way in a scatter plot to map text, right? You can't put in the y-axis a text value. And the other problem is, even if you could do that, scatter plots by their very nature have what we call the overdraw problem. And the overdraw problem is when you have multiple points on a scatter plot that are mapped to the same coordinates in that sort of planar space that a scatter plot uses. So I'm not going to go deep into scatter plots because we just did that a couple of weeks back. So there's a link to that exploration of scatter plots, which also includes a recorded live stream like this. So if you're interested in scatter plots, go explore that link. But what we want to do instead is we want to use these distribution visualizations. So here's a sort of typical visualization, what's known as a histogram. A histogram takes the underlying distribution of the data. So if you squint, you can see, like when we say almost no chance over here, this gold value, you can see that it's falling in this region between 1 and 5 and maybe 10%. And what we've done with the histogram is we've binned that into a region here between 0 and 5%. So we can see that 26 respondents said that almost no chance is a value between 0.05 and 3%. Now, why does it say 0.05 to 3 when I hover over it, but it says 0 to 5 down here? Well, 0 to 5 is the bin. This is the bucket that we've dropped those respondents into. But that doesn't mean that there was a 0 and there was a 5. If you actually look at the individual data points, you find out that nobody actually said 0 for almost no chance. They said 0.5% and up to 3%. So nobody also said 5%. Distribution visualizations. If we wanted to, we could reduce this to 10 bins, or we could bring it up to 30 bins, so you could have higher and lower resolution data. You could get down to 5 bins and see a very rough view of the data. And I found using this data set that I liked 20 bins. So there's no perfect number of bins. There are some techniques. There are some libraries and mathematical approaches to try to guess at the right number of bins that you could use. I'm not going to get into that in too much detail, but you can explore that. For instance, if you're familiar with the D3 histogram functionality, you'll see that they implement different kinds of binning strategies, automatic binning strategies. But in my experience, it's typically best for the user to describe the number of bins, because what you want to do is you want to adjust that number of bins depending on, say, the screen real estate, but also the kind of audience that you have.
Elijah, real quick, sorry. I think we have a little bit of technical difficulties, and you kind of went in and out there on a little bit of that. Wow. And so I think we just missed a little bit of the explanation of the audio side of it, and the video fine, but of the bins themselves. So you mind just kind of repeating that? Like what exactly, when you're changing the bin configuration on the right there, what exactly was that affecting in the visualization?
Absolutely. Sorry about technical difficulties. That is sometimes a problem of these live streams. So when we adjust the number of bins, what's going on here is we're adjusting the number of thresholds in a visual in a distribution visualization like this. And so you can see that the number of thresholds changes. And what this visualization is doing is it's taking each of these individual responses and it is compiling them into these individual bins in this visualization. So you'll see that the rough structure, the rough pattern maintains regardless of how many bins we use. But that as we lower the number of bins, we get naturally more points. And so it's the number of bins. There is no right number of bins. The number of bins simply determines the number of buckets or thresholds into which the points are tallied for a distribution. And you'll also notice that once you get up to a high number of bins, sometimes you'll get an empty, a blank column in a histogram visualization like this, a blank column where it seems like there is a distribution throughout this point. And that's because eventually the bins become so granular that there are no points being dropped into that bin, right? We have this bin over here clearly that is so granular that none of the points fall within whatever this value is, somewhere between, it looks like 77 and 80. And so that's one of the things to look out for when you're trying to optimize the number of bins for your display. Does that make sense, Dave?
Yeah, it's very helpful. Thanks. And in this case, obviously, since the kind of the value of the x-axis here is percentage is 0 to 100, we're seeing that if you pick, the 5 bins or 10 bins or 15 bins or 20 bins, it's giving us kind of, logical numbers for what's being divided. But if this distribution was, from 0 to 857, and you pick 20 bins, again, like the bins are not necessarily related to the to the values of what's on the x-axis there, but they're just dividing that whole, the whole axis up either 20 times or 30 times or 10 times or etc. Okay. Exactly.
It's taking the steps, the thresholds, and it's basing the thresholds off of typically an even division of the maximum value of your data set. There are some more advanced techniques that maybe don't have even distributions. They try to settle on what they call nice values, but even those typically try to come up with equal sized bins. They might end up saying you want 17 bins or 13 bins instead of something clean like 10 bins or 5 bins or 20 bins.
Perfect.
So go ahead.
I was saying that's great. Thank you.
Yeah. And so if we look at the distribution, we can actually see some interesting patterns here, right? We can see that, like we saw in the scatter plot, that most people agree that about even is somewhere around 50%. We can see that almost no chance, most people think that that's less than 5%, but we can see some people, or at least one person, thinks that's up to 15%. And then you see very interesting patterns for some of these other responses, like we doubt. Some people think we doubt means that it's not going to happen at all. And some people think we doubt. Some people are very optimistic about the term we doubt. And I guess they come from a very polite culture where somebody says we doubt, but really they mean that it's going to happen. And the same with probably not. Like, this is very interesting to me as sort of someone who works with statistics and someone who works with patterns like these, to find out that when we talk about whether or not something's going to happen, that we might have very different we express the same thing, but have very different beliefs about what that thing means. Dave, as you know, I have a philosophy background. This was a famous argument by a famous philosopher named Wittgenstein, that we have no arguments, that actually we just have differences in what we think the language that we're using means, and that's what results in arguments. And this data set sure seems to back that up. So that's a histogram, and a histogram is like a bar chart, but a histogram isn't a bar chart, because what a bar chart does is a bar chart bins values by some semantic dimension within the data. So you could create a bar chart like this if you grouped this data with like a SQL query into these bins, and then you could present it on a bar chart. But what defines these distribution visualizations is that dynamic binning, that dynamic thresholding that goes on. And so,
is this on this point real quick, because this is definitely one of the things that I learned a lot about, right? Thanks to working with you and kind of getting exposed to this type of visualization. I think I had always previously referred to as a histogram as just a bar chart, right? Where it just, it plots the bar chart, and I'm doing a count basically for the y-axis. And it was a bar chart, but I'd always would kind of call that a histogram and think of that as a histogram. And I think it's helpful just talking a little bit about what what separates the histogram from a bar chart. That was very helpful. Thank you.
Yeah, and that's because, when it comes to data visualization, you just like natural language. We have 26 letters in the alphabet, but we can use those 26 letters to spell a lot of different words. Well, we have an alphabet of shapes in data visualization. So we have rectangles, and we have circles, and we have lines. And we can use those things to make a lot of different charts. And so you end up in a situation like this, where you have a histogram, and you think, oh, well, this is just a bar chart. And if I had this as just a single category here, that might even, that would look very much like a bar chart. And what these distribution visualizations allow you to do is very easily sort of compile the distributions across each other. You see it less often with a histogram. Histograms oftentimes you see with a single category instead of like I've done here with this dozen or so categories. So histogram is one way to do it, and a histogram encodes the magnitude of the bin in the height of the rectangle. So that's the same way that a bar chart encodes value in the height of a rectangle or the length of a rectangle. A heat map showing exactly the same data encodes that value in the saturation of the color. So here we see the same data set. And what jumps out at you, of course, is this about even bin here. And so instead of it being a very tall rectangle, instead it's a very saturated rectangle. And so a heat map is another approach that's a common approach. And you could imagine different times when you want to show heat maps versus histograms. Heat maps very much because we're using saturation, the low values recede much more. And so there's a lot more visual noise over here for these outlier kind of values. Whereas a heat map, those fade almost to imperceptibility. In fact, you might not even see it on your screen because you're looking at this through a live stream. And so what it lets you do is it lets you focus more on the denser regions, the hotter regions. And so heat maps, sometimes heat maps typically use saturation. Sometimes they'll use color even.
And just a quick point here. I mean, just to reemphasize it, the approach that we're taking here in the heat map of binning is the exact same as what we just saw with histograms, right? So this is just about how you represent the value or the count within each bin.
Exactly. It uses, in fact, exactly the same functionality under the hood. Exactly the same techniques are used to bin the values, and then we just use a different method to display the values. And that's pretty, that I think makes a lot of sense to folks because they're rectangles, right? And in one case, we're making the rectangle change its size. In the other case, we're making the rectangle change its color. What probably people don't expect is that when we look at something like this, which is what's known as a violin plot, that this uses the same technique under the hood as well. So what's going on with a violin plot is we've got the same kind of thing that's going on with a histogram, where the width of the shape determines the magnitude of the distribution at that point. Except here we're connecting the shapes and using a sort of curved connector. Then it ends up looking like a violin or a lute or guitar or any sort of instrument like that. And that's why they're known as violin plots. And so we're, again, showing exactly the same data using the same technique under the hood. Now, this has more bins. Actually, it has the same number of bins. Good. But what we also can do with a violin plot, what you also sometimes see with a violin plot is this little blue line, this little dark line inside the violin plot. And what that's showing in a violin plot is something called the interquartile range. I'm going to get into a little more detail with this in Boxplots. But basically, the interquartile range of a distribution is the points within that distribution that are between 25 and 75% of the distribution. So what it's showing you is the middle of the distribution. And that's interesting when you're trying to understand distributions because it tells you something about how normal this distribution is. It tells you something about the shape of the distribution. So if we look, we see that like a distribution like this for highly unlikely, that 50% of the value is in this single bin here. And it's got a very long tail out to the right. So that tells a story with that distribution. We can see over here with about even that the interquartile range, because it's all fixed on a single point, that there isn't even an interquartile range for it to display. And then we can see over some much of the distribution and talks to you about you can't make claims about how much agreement folks have about this term as you could about, say, the terms up here, right? What's really interesting to me, of course, is the little chance most of the it's a very broad, flat distribution. Most of it is between 10 and 20%. But then there's this fat part over here. So this is a very interesting sort of distribution story where most people think that it's less than 20%, but there's a lot of folks who think that it's actually more than 20%. And those are the kind of stories you can look for in distributions. You get the same sort of fat part over here and probably not. I always feel like whenever I look at this data set that this is like the Midwestern cluster, right? A lot of very polite people who think that probably not still is going to happen, or they're just very optimistic folks.
I mean, I'm from Minnesota, and I will say probably not. It just means slightly less than 50%. I mean, there's still a chance it's going to happen, right?
I mean, clearly, that's what it means. I mean, to me, and I don't want to get too deep into this because this is about data visualization. The story here about ambiguity of language, even highly technical language, which we have to think about, probabilities are technical language, is something we deal with throughout our lives, and we sort of lose track of when we're trying to live in a nice, clean world where this kind of stuff doesn't happen. Where we all agree on what words mean. So violin plot, histogram, heat map, all of them are using the same technique under the hood. They're all using this binning technique. Now let's look at a box plot. A box plot doesn't do that. A box plot derives shape.
Ooh, Elijah, just real quick, when you come back, we lost the audio.
Of a glyph.
So Elijah, sorry, we lost the audio right when you said what a box plot was doing. So I just want to make sure we replay that one because that's going to be the important part to start this off.
Excellent. So we're having just a great time with the audio today. So so far these live streams have been pretty technically clean, and we'll have to do a distribution of audio quality of our live streams at some point.
Yeah.
So a box plot, unlike or any of the distribution visualizations we've looked at, doesn't use binning. What a box plot uses is it uses the data itself to create the shape. And what I mean by that is that the individual glyphs of a box plot, and a glyph just means a graphical shape that's made up of multiple marks, made up of multiple individual pieces of graphical content. The glyph for a box plot is based on measurements of the quartiles of the data. So we talked about interquartile range. In this case, the quartiles, the 4 quarters of the data, are the first 25%, the second 25%, the third 25%, and the last 25%. So 0 to 25, 25 to 50, 50 to 75, and 75 to 100. And what a box plot encodes is it encodes the minimum, that's the bottom whisker here, the interquartile range, that's the fat part of the box plot here, the median, that's the dark line in the middle, and then the maximum, which is the whisker on the other side. And so box plots show you the shape of the interquartile range with the median, and then they show you the minimum and maximum. And that's super valuable for understanding weights of distribution in a very clear way. We can see a lot of things that we saw earlier really jumping out to us. For instance, the median value over in highly unlikely is 5%, even though there's definitely a really absurd maximum. But the interquartile range will go all the way up to 10%.
Yeah, I think like one of the things that just jumps out immediately is the kind of absurd min and max for some of these, right? Like that you see in this chart that you wouldn't necessarily see in some of the other charts.
That's right. That's right. You'll notice them, but because the weight of the visual space is on the distribution, the fat part of the distribution, these you sort of don't they don't jump out to you as much. Yep. Whereas a box plot, because of how that glyph works, it's really telling you, it's really drawing this line. Right? It's drawing your attention to those min and max. Now, one of the things, just like an interquartile range being shown on a violin plot, one of the things we can do with a box plot, a typical technique, is to show it without drawing those whiskers out to the min and max. and instead presenting values as outliers if they go beyond 1.5 times the interquartile range. So this is just a definitional way of searching for outliers, this idea that anything that's beyond 1.5 times the interquartile range is an outlier. And you can see that suddenly these box plots become a little less hairy. Now, one of them, right, the one for we believe, shows that actually it's chance and highly unlikely. They show that no, we've got really like serious outliers out here, right? We've got some serious points that are way beyond what most of the respondents have. And what's interesting is, of course, when you have that definition, then if you have a distribution like about even, that's a very tight distribution, then almost everything that's not within that tight distribution is an outlier. So most people said that about even is 50%, and anybody who didn't is an outlier in that case, because the definition of outliers is dependent on the distribution. So box plots are great if your audience understands them. They can be very challenging if they don't. The outlier presentation of outliers is super important because you want your audience to become accustomed to the concept of outliers and anomalies, because that allows you to get to higher order explorations of data patterns. So try to proselytize box plots and things like that, because they simultaneously display data, but also build data literacy so that people start to understand what we mean by outliers and quartiles and things like that. Now, these charts are pretty common: histograms, heat maps, violin plots, and box plots. Less common charts are charts like these ridgeline charts. And a ridgeline chart is like a histogram, except we've drawn the shape like we have with a violin plot as a sort of curved shape. And the thing that ridgeline plots are known for is that you'll see that they actually draw over the column behind them. And so you end up with these really emphasizing these peaks like we have here with about even. About even is so dense that it's actually, overflowed into half of the probably not column. And so this is a striking visual way of showing distributions. It's especially good for showing multiple distributions simultaneously in a way that sort of catches people's eyes. It pays for that by being less precise. And so this isn't something that you can put in front of folks, and they will be able to make as precise decisions and calculations as they could with some of the other forms we've already shown. But we know from these earlier live streams, I know from my experience with data visualization, that sometimes just getting people to look at a chart is valuable. And so you want to try to draw people in, because even if you make this great, scientifically accurate, extremely precise chart or dashboard, and nobody looks at it, then it doesn't have as much value as a chart that maybe isn't as precise, but at least you got people to look at it and to start to think about the patterns that chart is showing.
As a quick question, Elijah, I know for the first couple of charts we talked about, it was using that the binning approach, right, to determine the where to put the visualization there. And then we learned in box plots that it was, inferring from the data itself the interquartile range, and then drawing the whiskers and the outliers. How about ridgeline here? Is it back to the binning approach, or is it more in line with like a box plot style of it's inferring from the data?
Yeah. So the ridgeline is back to the binning approach.
Okay.
And you can tell that it's, in fact, if you really sort of squint and flip between a ridgeline and a violin plot, you'll realize it's the same thing. That if I took this violin plot and I cut it in half and I exaggerated that curve, that I'd end up with one of these ridgeline plots.
Got it. And so again, it's like, I don't know the right way of phrasing this, but the actual kind of slope you see on that ridge line is, I think you mentioned this, we talked about the precision. It's not the exact if you were
It
plotting
is
like
accurate. It's encoding it. It's encoding it based on the magnitude of the data, but
yeah.
it's exaggerating it beyond the column size. And as a
Okay,
result of exaggerating it beyond the column size, it can be harder to read.
gotcha. There we go.
It
Yeah,
can be harder for people to make the sort of, because you cannot go sort of, you can't scan side to side and use those columns as sort of like your cognitive guidepost on what the magnitude is being encoded. And so you can get into these points where you're like, oh, well, this is getting to the very top of the column, so that must be, you know, the peak. And you're like, no, actually, it peaks somewhere above the column. And so that can be, you know, that's putting a cognitive load on your user or your reader that's going to make this less precise as a result, even though the actual shapes are direct representations of the data magnitude.
gotcha. Very helpful. Thank you.
Yeah. And an even less common chart is what's known as a horizon plot. And a horizon plot is also a binned distribution plot. And a horizon plot is interesting in that it's kind of a mix of other charts. It's kind of a heat map, and it's kind of a violin plot. And so in that way, what a horizon chart does is it has these thresholds. So 1 to 10, 10 to 20, 21 to 31, 31 to 41. That it is using to encode different colors in these peaks in your distribution. So this very light color means that whenever you're looking at it, it's a value between 1 and 10. And you can go see that like this is 4, and over here we've hit 10. And so it goes from it encodes magnitude using saturation or you know, sort of color depth, like from light to dark. And then it further encodes the steps within those thresholds using height. And so a horizon plot is great, just like a heat map for seeing these very dense regions. What it has over a heat map is it gives you a little bit better of an understanding of the variation within those regions, because it allows you to use thresholded colors, so you don't just go from a very light to a very dark continuously. And you end up in these situations where if you have density, you'll see this sort of compounding color drawing on top of each other. So you can see that there's this sort of darker blue over the medium blue over the light blue. And that shows you these regions of density within your distribution. So again, a horizon plot, like a ridgeline plot, is going to be an exotic chart. But in being an exotic chart, it might be something that draws people in. It might be something that resonates with certain audiences in a way that these other charts might not. And so besides my wonderful distribution pun at the bottom of this notebook, those are the charts I wanted to walk through. One of the points I wanted to really emphasize that I think we did was that, you know, there's a lot of the same techniques being used. Even though Boxplot uses a very different technique, it's still based on quartiles, and quartiles show up in that interquartile range within Violin Plots. You'll see sort of this concept of outliers in distribution visualization, and I think that, you know, there are many different ways to visualize data. There are many different ways to visualize distributions, particularly. And which one you choose is dependent not just on what the most, quote, precise or effective, there is no best distribution visualization. Rather, there are different options that are going to be suited for different purposes and different audiences.
Perfect. Yeah, thank you so much, Elijah. I mean, we're a little over 30 minutes here, so I think we'll wrap it up here. But I thought this was an excellent overview of these different visualization types. You know, like I've mentioned to you before, I have learned a ton from working with you and getting exposed to these, because these were, you know, again, coming from my background, I kind of always had, you know, misstated bar charts as histograms, and really learning a lot about the different types of distribution charts that Dex and Notable provides has been incredibly enlightening. So hopefully everyone here has learned from this and can benefit from it. And again, our apologies for some of the technical difficulties when Elijah's audio kind of there was some gaps in it during the video, so again, apologies for that. But if you have any questions on this, please feel free to reach out to us. This notebook, the link will be shared, and it'll be publicly available. And so if you have any questions, please comment on the notebook, or contact us, reach out to Elijah with any additional questions. And we will be back again in a week, right, Elijah, for another Data Viz Friday.
Right. Yeah. See everybody next Friday. Thanks, folks.